All right, welcome back. For me, it's like 5 minutes later, and again, it's like 2:30 in the morning. Oh, my schedule is very strange. All right, so if I just seem a little bit out of it, I am. All right, we talked about recognizing or forcing the pattern, like the chain rule type pattern, to undo chain rule to take the integral of a function that has an inside function, essentially. Now we're going to learn method 2, how to use formal use substitution. To do that, again, you could always use formal use substitution, but it's usually harder and not necessary for many problems. Okay, so we're going to start with example 5. Again, the book for examples 4, 5, and 6 uses formal use substitution for all of them, but only 5 is necessary. So I'm not doing it on ones that are not necessary, which I would hope that you would emulate that. So again, this is page 336 in your book. They want you to find the integral of x square root 2x minus 1 dx. All right, on the surface, doesn't look so bad. If we tried to force it, right, which is actually the same way you would start formal use substitution, what is like the inside is? The thing under the square root. That's what it looks like. Looks like this would be your u. So it looks like we'd say u equals 2x minus 1. You wouldn't be wrong. Again, u puns. You wouldn't be wrong. Then you would take the derivative of this. And I'm calling it, again, I set this up before on purpose. I'm calling this du dx instead of u prime for a reason. So I want you to do the same thing. So du dx is 2. All right. What you need is 2. What you have, the extra thing, right? Because we have the inside function and the square root over the inside function. That's our outside function. That's fine. But the extra thing that you have besides that in your integrand is an x. So what you have, right? Well, those are not different by a constant multiple. In fact, I would have to change an x into a 2, I would have to multiply by 2. That's not the problem. But then I'd have to divide by an x, which means the outside I'd have to multiply by an x. But what did I tell you before? Side note, never put an expression with an x outside the integral. No, no, no. You can't do it, right? So you can't do that, right? So these do not just differ by a constant multiple. They differ by like some x expression, right? So these have different powers of x, different, not just different by a constant multiple, not just different by a constant multiple. Therefore, right, remember these 3 dots mean therefore. Therefore, you cannot even force the pattern. You cannot even force the pattern. So method number 1 is impossible. So you must use method number 2, which is U substitution, formal U substitution. All right. Well, I'll keep this down here if people are copying this down. You have to use formal U substitution. So I'm going to show you what that means. Well, that generally means we've kind of set the framework, but usually we got to the U, identifying the du dx, then identifying the outside function, and then just kind of like, just kind of writing down the answer still in terms of x, right? And we talked about like the outside function in terms of like, oh, what's being done to the blob? Oh, it's like blob squared, so that becomes blob to the third over 3 or whatever. That kind of lingo is just kind of teetering around formal U substitution because the idea is the same. It's just kind of less writing and less formality about it. So to do formal U substitution, right? So now we need formal U substitution. So we did the U, we did the du dx. Now, so for formal U substitution, essentially you need to write down your U, you need to write down your du dx. Then here's the other part. Now you have to substitute everything out, everything after the integral sign, even including the dx. You got to get rid of anything that has anything to do with x and substitute it in terms of u, right? So then your third step, nope. Your third step, sub out anything with an x in it after the integral sign in terms of u. Sub out all x expressions to be written in terms of u. That's why it's called formal U substitution. This is where you actually have to go all the way with u. Again, the u puns. So before we identified what we called a u, we said du dx, but that was just kind of a tool to then help us like frame what we know to be our inside-outside function and then kind of write the answer. This time, we're not joking around. We're literally going to substitute out anything that has an x to be written in terms of u. Okay, and how are we going to do that? This is how, right? This is our framework. This is how we know how u is related to x, and how we know dx is related to du. That's why we wrote the derivative u in terms of du over dx, not as u prime. In fact, when we do differential equations in chapter 6, we're also going to do this as well. We're not going to write primes. We did this with implicit differentiation too, where I said do not write primes. Write it out with like, dy dt or whatever. Okay, so what we're going to do, we go through here and can literally just start with what do we see, right? First, we see an x. I can't write an x. I have to write that in terms of u. Well, what is x in terms of u? Okay, well, that means I'm going to have to figure out what is x in terms of u, right? So if u equals 2x minus 1, that means u plus 1 equals 2x, and therefore x is going to equal u plus 1 over 2, right? Okay, so that means this u plus 1 over 2 is what? Let me do that. This is going to get subbed in for this x. Now this is easy enough. What's going to get subbed in for the 2x minus 1? A u, because that's literally what we defined our u to be. That's easy enough. And we're going to have a square root over the u. That's fine. Now, what are we going to sub in for the, right? So we have kind of three things we're subbing in. We got to sub in something in terms of the x. We got to sub in something in terms of the 2x minus 1, which is just going to be our u by definition, what we already have written down there. But then we also have to sub in something in terms of dx that has an x in it. It can't have an x, it has to have a u. So what is dx going to be? Right? So we need to use this to rewrite what dx is going to be. Well, you're literally going to use algebra and you're going to multiply this side by dx, this side by dx, and you would get du equals 2 dx, and then you would divide. You want to know, right, kind of like literally in substitution when you're doing like linear systems of equations, right? You want to isolate dx, know what it's equivalent to in terms of du, and then sub back in. So now we're dividing both sides by 2. So this means dx is equivalent to du over 2. So what does that mean? It means this du over 2 is going to get plugged in for our dx. So what does this look like? I wish I could move that little bar thingy. I don't know if I can. So now we have, instead of x, we have u plus 1 over 2. So here we have u plus 1 over 2. Instead of root 2x minus 1, we have square root of u. So this is times square root of u. Instead of dx, or dx is equivalent to du over 2. So we have a du over 2. Okay, I'll zoom out. So do you see that? Our x, I'll just use the laser pointer. Our x became our u plus 1 over 2. Our square root of 2x minus 1 became our square root of u. Our dx became du over 2. All based on what we defined to be u, therefore what the derivative of u with respect to x was, a little bit of algebraic manipulation over here and over here. So we substituted anything that had an x in it in terms of what had a u in it. Every single thing had to go, including the dx. Okay, let me rewrite this little one. It's kind of bothering me. Plus 1. Okay. Too much. Plus 1. Okay. So now, what in the world, prof? What are we doing? So now, for now, we can kind of ignore the fact that we have u's instead of x's, right? U is just kind of like a dummy variable, right? Treat u like a dummy variable just like you would x, right? So u is just a, what we call a dummy variable, right? So there's nothing special about u. You just treat it like you would x. Okay, now, just like with any integral, right? You have the integral sign in the front and you have a d, whatever your variable you're integrating with respect to. So here we have du because everything else in the integral is in terms of u's. All right, so we have our integral. We have our du at the end. What in the world's going on in the middle? First of all, we have, actually I'm going to delete this. We have divided by 2 twice. You know what? I'm just going to pull those out to make that a 1/4 out here. Hopefully everyone agrees with that. Right? Any constant multiples, not this like u plus 1 thing. You can never do like a +1 and move it outside the integral. That's not a thing. No. All right. But those constant multipliers of 1/2 times 1/2, which is 1/4, just move it outside the integral. That's fine. And then the rest here, we have square root of u times u plus 1. You know what we can do? We can distribute. So actually, let me write that in green. Part of what makes, again, this is part of why I like this. That's all kind of like a puzzle, and every problem is kind of different. And you just kind of have to use your problem solving skills, your math, kind of every little intuition thing in calculus that you've learned. Because if I just said, okay, integrate u plus 1 times square root of u du, right? Your mind might be going crazy, like, what? Okay, are we looking for some inside function here? And then how's a square root? Like your mind might be going crazy. But hopefully you remember like way back to when we first started doing even derivatives, right? And if you had written that I want you to take the derivative of in parentheses x plus 1 in parentheses times square root of x, right? At first you might be thinking, oh man, well that stinks. I'm going to have to do like a product rule thing, blah, 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 right? And we said, no, you don't need product rule for that. You just, right? Square root of x is just like x to the 1/2 and you like multiply it out. Oh yeah, that's so much easier, right? So here, not only is it easier, but it's like required. If you don't multiply it out and use some critical thinking, you're going to be stuck, okay? All right, so what do we have when we multiply this out? Again, this is like u to the 1/2. Let me just write this up here. Equals u to the 1/2. Hopefully you can see that, 1/2. Right, so u times u to the 1/2 is u to the 3/2 plus u to the 1/2 du. Right? Again, if you need to pause the video and have the sub or a classmate like explain if people are like super confused, feel free to do that. Well, hopefully at this point, so again, we can still just stay in terms of u, right? Before we jumped very quickly into the solution, what's the outside function, talking about blops, that we did the antiderivative quickly, blah, blah, blah. Here, you just take your time, keep following the steps, all right? We're still in terms of u, that's fine. Now our final answer, we don't want to put in terms of u, but until we get to that stage, we're fine to be in terms of u. The 1/4 stays here. Right, now your integrand is something nice and easy, right? You can take the antiderivative of a variable to the 3/2 and a variable to the 1/2. That's fine, you know how to take the antiderivative of that. It's just inverse power rule. All right, and this is the 1/2, the 1/4 applies to everything in there. So u to the 3/2 plus, so 3/2 plus 1 is 5/2. Excuse me, be careful. U to the 5/2 over 5/2 plus u to the 3/2 over 3/2. And I can go ahead and say plus c. Now we're not going to write, this is our final answer. You do not, right? This is important. All right. You do not keep final answer in terms of u, or do not write final answer. Do not of u. You must plug back in for x. Okay. Super important. All right. So, well, what even is our x, you ask? Come back up here. every u that you see is going to be 2x minus 1, right? This is where we had like the blop thing, right? Again, this is just helpful notation so we don't have to hold all these complex things in our mind while we do some like little algebra stuff. Think of the antiderivatives, and then a few steps later, then we plug back in our quote-unquote blop. So our quote-unquote blop, aka our u, is 2x minus 1. So 1/4. And I'm going to go ahead and write this as 2/5. 2x minus 1 to the 5 halves plus 2x minus 1 to the, oh, I forgot the 2/3 thingy, plus 2/3 to the 3 halves plus c. Technically here, I don't know if we've talked about this. The 1/4, probably some people are asking, why? Probably asking, why does the 1/4 not distribute to the c? The c just means unknown constant. You could write it as having the 1/4 distribute to the c. It's common convention to leave out the c from any, like if it's something like this and c is its own term, it's like plus c, to leave it out from distributing the 1/4 to it. You'll see in 6.2 and 6.3, we actually even are allowed to change what c means throughout the problem. If we change it consistently, you'll see it's kind of weird. Okay, so let's just tidy this up a little bit. 2 and the 4 cancel a little bit, so we got a 2 on the bottom. I mean, yeah, 2 on the bottom, so it looks like a 1/10. Yeah, okay, good. I haven't looked back at the answer thing for a while, so I'm glad we're doing it right. 1/10, 2x minus 1 to the 5 halves plus, let's go ahead and distribute here. Looks like that's going to be a 1/6 once we cancel a little bit. 1/6, 2x minus 1 to the 3 halves plus c. That's it. Okay. The next thing we need to do, the next thing I'm going to do is I'm going to show you how to do formal u substitution on a definite integral where you have bounds. That's not difficult, but it's something you have to stay consistent in, and there will have AP questions every now and then that makes you the test that you know exactly how to do this. So unfortunately you can't get around it because there is kind of a shortcut to get around it, but if you're given a choice. Then we're going to do number 9, example 9, which I actually do differently than the book does. I think the book overcomplicates it. And I'm going to do homework problem number 111 as an example of one of the harder homework problems where you have to use formal u substitution. And then I'm finally going to end this video and go get something to eat and go to sleep. Fun fact, I actually, especially since this is my last pregnancy, on Black Friday this year, I found a Groupon deal for a prenatal massage. So I have that booked for tomorrow. So I'm pretty excited about that. Anyways. Okay. All right. We said we're doing, all right, so I'm going to do example 8 on page 339. I'm going to go through it fairly quickly. The big thing I'm focusing on here So this is example 8, page 339. Big thing I'm focusing on here is the bounds of if you either by choice or by necessity of it being an AP problem and they ask the question in a weird way, which it will come up. You have to continue doing all the way U substitution until the end, right? Because notice here we had an indefinite integral and we did end up eventually plugging back in the expression, so like here we had our u's and I said, do not write the final answer in terms of u, you must plug back in for x. That is true if you have an indefinite integral. If you have a definite integral and there's bounds, and so instead of having a plus c, if you're plugging in like bounds, generally speaking, you would have two choices. You would have one choice where you can plug back in for u, plug back in the x expression, and use the original bounds. Which here, well, there's no bounds here. Or if you stick to your guns, you say, I'm going all the way in u's, I'm not turning back, I'm not subbing back in for x, I'm just going to use u. That means you have to change your bounds to show that your new bounds are now u bounds instead of x bounds. Okay, so example 8. 0 to 1. So this one is actually pretty simple. See, like if I were just given this and given free reign of what I should do, hopefully you could fairly easily see, oh yeah, I could force the pattern here. Our u would be x squared plus 1. Our du dx would be 2x. Oh, it's only off by a factor of 2, multiple of 2. Great. Put the 2 next to the x, put a 1/2 outside, and then hopefully you could use your imagination where instead of doing the plus c for the indefinite integral, for the definite integral with bounds 0 to 1, I could then take the antiderivative, right? My outside function is blob to the third, antiderivative is blob to the fourth. So I could rewrite this whole thing as x squared plus 1 all to the fourth over 4, but also times the 1/2 from before, plug in a 1, that whole thing, plug in a 0, subtract the 2, bada bing, bada boom, it'll be done. But we're going to do this in a way that we use formal U substitution. We go all the way in U substitution. We don't plug back in for x ever. Point of no return. Okay, so we're going to do it. So, so this is formal U substitution. So solving an indefinite integral with formal U substitution without back substitution, essentially. So this is a definite integral solved with formal U substitution. Right, definite integral meaning there's bounds. Solve with formal U substitution and no back substitution and back into x's. Back in. Right? So we keep the u's, all the way keep the u's, which means we have to change our bounds to be in terms of u. All right, so again, this is not necessary to do in terms of u substitution, but we're going to do it to illustrate a point. Formal u substitution. Here we go. This is our u. Our u is x squared plus 1. Our du dx. My computer is getting tired too. Du dx It's 2x, right? Now, what we have is 2x. What we need is x. But instead of doing the like times 2 times 1/2 on the outside, guess you could do that. But when we have formal u substitution, what we really mean is what we're going to do. So obviously the x squared plus 1 is going to be sub back in for u. What we have left, right? So this we have left. So we need to also, right, need to know what x dx is in terms of u, right? So because we have to remember for formal u substitution, everything after the integral sign has to go to be in terms of u. So we can use a combination of the u that we know and the du dx that we know, right? But the du dx is going to be more helpful because it has the dx. So we're going to do some algebra here. So I'm going to multiply both sides by dx. Dx, all right. So what's that going to do? That means I have du equals 2x dx. Now that's almost what we need. What we need is x dx. So this is what we need. Right, so I'm going to divide both sides by 2. So I'm going to say du over 2 equals, oh, that's not equal. I hate it when people do that. Don't do that. I'm just going to draw an arrow, meaning this is the direction I'm rewriting this formula in. That looks like a 9 or something. Du over 2 equals x dx, right? So this, oh come on, this x dx gets subbed out for du over 2, right? Du over 2 is equal to x dx. Okay, so, oops, come on. All right, so where are we at now? I'm going to come back to the bounds because we cannot write the 0 and the 1 as bounds any longer. So now everything in terms of u. So the x dx became, whoa, come on, that's not what I wanted. The x dx became du over 2. So I'm going to write that at the end. Du over 2. That's the whole x dx. X squared plus 1 is equivalent to u, so I can rewrite that as u cubed. Okay. Hopefully you understand that, right? That this is equivalent to this, and this got subbed out for this du over 2 thing. All right, now the bounds. Here's the big thing. Because, see, even at this point, even if we had used this formal u substitution to get us this far, we could have plugged back in right here in terms of x, kept our x bounds, and everything would work back out as long as we went back. Everything went back to being in terms of x. But sometimes some people like doing stuff in terms of u. Great, so you can just keep on sticking to your u as long as you're consistent, and here we have to change to u bounds. Or sometimes on the AP, they'll be tricky and make you think in terms of u bounds. So this is important. So now, if everything's in terms of u, that means we also need, actually let me, need bounds and converted to U bounds. Okay, if we're going to stick to our guns and stay with U, we have to have our bounds in terms of U. All right, how are we going to do that, Prof? Right, because before we went from x equals 0 to x equals 1. Well, when x equals 0, what does U equal? How do we figure that out? Right, again, here's our like decoder process. If we're going between x and u, if we're going between du and dx, this is our little decoder, encoder, whatever. So if our x started as, I guess we're starting with the lower bound 0. So when x equals 0, right, when this x equals 0, you plug in x equals 0, boom, you can know what u is. Okay, so when x equals 0, u equals 2, what is it, 2 times, no, x squared plus 1. So 0 squared plus 1, so u, well, let me just keep on going. U equals 1, so this is 1. Nope, just kidding, I wrote in the wrong space. This down here is 1. The lower bound is 1. The upper bound started as a 1. So when the upper bound started as 1, u equals 1 squared plus 1, which equals 2. So this becomes 2. Okay? And so you would just keep on doing the integral in terms of these new bounds now. And this 1/2 can be moved outside here. So 1/2 integral from 1 to 3 of u cubed du. And again, we can just stay in terms of u. We don't have to go back since we, why did I write 3? I don't know. Sorry, it's 2. Yeah, since we convert our bounds to even be u bounds, then we can keep on going. Okay, so 1/2 integer of u to the third is u to the fourth over 4. And we're not back substituting in terms of x, like I said. For this thing, we're going all the way. Since our answer is going to be a number, we don't have to ever back substitute as long as we use u bounds. Okay, 1/2 times u to the blah, 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 blah. But then this is going to be evaluated between 1 and 2. Technically, it doesn't really matter if that 1/2 you multiply by the 4 at the bottom and make that an 8, or you just keep it out as a 1/2 to the end. You could even, in this case, bring out the 4 in the denominator and multiply by the 2 because there's literally only one term. You couldn't do that, obviously, if there's more than one term. Anyways, we'll do it like this. So 1/2 times 2 to the 4th over 4 minus 1 to the 4th over 4. So 1/2 to the 4th is 16. So 16/4 is 4. Over 4 is 4. Minus 1/4. Whatever. Okay. 4 minus 1/4. Don't do mixed numbers. Don't say 3 3/4. What is 3 3/4? Well, 4 is 16/4, so 15/4 over 2. 1/2 times 15/4, which equals 15/8. Good, we're right. Okay. So you have to convert your bounds into u bounds if you're using formal substitution. And you're not back converting in terms of x. Okay. The next thing, okay, yeah, I said I'm going to do example 9, and then I'm going to do homework problem 111. Then I'm calling it a night. All right. Example 9. So these last two are just two more examples of like the difficult substitution-y things. I'm not going to give you very many of these. They're going to be fairly rare that you see them like this, that are this difficult, where you absolutely have to use formal use substitution. But you should know how to do them. You should know how to convert the bounds if there's definite integrals, etc. Example 9, this is on page 340. So I do this differently than the book. I think the book's way is just too gimmicky. Oh, sorry, I'm stretching my neck. Okay. Integral from 1 to 5, yeah. X or root 2x minus 1 dx. Okay, don't know why I made that division sign so long. Okay. Immediately I see this and say, so I'm trying to keep this near my mouth. I hope this is loud enough. I hope you can hear it. You pretty obviously, I mean, really the only option you have is that this would be your u. So u is 2x minus 1. So then du dx is 2. But again, what you have is an x. Does not differ by a constant multiplier. You cannot use. Right, so comparing these two, right? Cannot force the pattern, so you got to do formal use substitution. Okay. So what does that mean? That means I'm going to have to go back here. I need to know, well, what's left to take out in terms of to turn every x into u. What's still left is I'm going to take out this red circle thing here. What's still left is this x dx that needs to come out. So we need x dx in terms of u. Okay, to do that, I'm going to keep going with this thing. So, well, we can figure out what x is, dx is. So do dx. Hopefully you can see that du equals 2 dx, and then therefore dx equals du over 2. Okay, so this can go in, this goes in for dx, but we need something else to go in for x. Well, what goes in for x? Well, u plus 1 equals 2x and x. Oh, Silas. He knows I'm doing calculus, apparently. He likes to stay up late with his mommy, too, I guess. All right. X equals u plus 1 over 2. So this goes in terms of x. Oops, I just clouded out this 1. Okay. Now, yeah, they're going to change bounds and all that stuff. That's fine. We pretty much have to change the bounds. We can't really just fully back substitute because you can't force the pattern. So if you can't force the pattern, you might as well just go all the way in x. I mean, all the way in u. Okay, so we need to change the bounds. So change to u bounds. So when x equals, our bounds were 1 and 5. So x equals 1 when x equals 5. And our formula is u equals 2x minus 1. X equals 1, u equals 2 times 1 minus 1. What did I do that for? Which equals 2 minus 1, which is 1. When x is 5, u equals 2 times 5 minus 1, which equals 9. So the 1 stays 1 coincidentally. The 5 goes to a 9. Okay. Oh yeah, the book does this like in a strange way. So if I were you, I would ignore the book. I mean, the book's way's not wrong. It's just they let u equal the square root of 2x minus 1, which, sure, if you're consistent, that can work, but I mean, why that? You would always tend to choose the u to be what's inside the square root, so I don't know why you would. There's no need to go against that in this case. All right. So this whole thing. So we changed our bounds. All right, so we now are going, and note, just be careful because sometimes when you change the u bounds, like here our lower bound was 1, our upper bound was 5, and it changes to our lower bound's 1, our upper bound's 9. Sometimes when you change your u bounds, actually, like here, it could change like a 1, maybe changes to a 7, and the 5 changes to like a -2. So instead of going from 1 to 5, you could technically have a lower bound of 7 and an upper bound of -2. Hopefully you remember from properties of integrals we learned before, you can flip the bounds back so that they're like lowest to highest, but then you put a negative sign out front. Okay, keep that in mind. So this now is from 1 to 9. Okay, what do we sub out? Our x became u plus 1 over 2. U plus 1 over 2 was the value of our x. Now this is important. So our 2x minus 1 is our u, but that was 1 over the square root of that u. 1 over the square root of u. I can write that like that for now, but then we're going to want to, right? So this is 1 over the square root of u. We're going to rewrite that in a second. It looks kind of sketched like a 4. Okay, times our dx. Again, you can't take for granted. You can't just assume dx is equal to du. It's not, usually isn't. Our dx is equal to du over 2. So du over 2. All right, so that's everything subbed out for in terms of u. Our bounds, our x, our 1 over root 2x minus 1, our dx. Okay, so now that we have everything converted, we can just finish this problem as it is. Let's rewrite this. First of all, the 2's can come out. I'd pull them out there. So I'd do like a 1/4 thing. I'm going to rewrite this before we start taking antiderivatives. The 1 over square root u, hopefully you can recognize that as u to the -1/2. This is u plus 1 times u to the -1/2 du. Okay, 1/4. So again, you're going to distribute this. There's no way to solve it otherwise. So u to the 1 times u to the -1/2. Add the exponent, so you get u to the +1/2. And then 1 times u to the -1/2 is just u to the -1/2 du. Right, these are just reverse power rule things, so 1/4 u to the 3/2 over 3/2 plus u to the 1/2 over 1/2, evaluated between 1 and 9. and you're just going to directly plug that in. So 1/4, and just be super careful with this. So I'm going to have 9, let's see, 2/3 times 9⁵ minus, nope, just kidding, plus 2 times 9⁻⁴ in parentheses minus, start new parentheses, and then we plug in 1, 2/3 times 1⁵ plus 2 times 1⁻⁴ in parentheses in brackets. So 1/4, let's see, 9⁵ square root of 9 is 3, 3⁵ is 27. 27 2/3 times 27 plus 2 times 3 minus 2/3 plus 2. It's not that bad. If you do the math, skipping on down, should be 16/3. Okay. The last one I'm going to do, or at least get you started on, is homework number 111. Homework page 343, number 111. All right. This one's just tricky. 1 to 2, x minus 1, root 2 minus x dx. Okay, again, we get this one started. And it's pretty, nope, that's not what I said. It's pretty obvious that this has to be the inside function. So our u has to equal 2 minus x. Our du dx equals -1. Okay. And this is not -1, is not a constant multiplier of x minus 1. Have to use formal u substitution. Okay. So we need to write x minus 1 in terms of u, and we have to write dx in terms of du. Okay, well that's pretty easy because in this equation, right, du equals negative dx. So therefore, negative du would equal dx. Okay, so we know, plug in that for that. We already know we plug in u for 2 minus x, so it's going to be square root of u, easy peasy. X minus 1, so we need to know what x minus 1 is. Well, how do we do that? We need to rearrange this thing to not be in terms of x, but to be in terms of x, well, either in terms of x minus 1, or I guess we can do it in terms of x and then just subtract 1, doesn't matter. So if we add x to both sides, we would get x plus u equals 2. So x equals 2 minus u. So fine, that's not a 4. So u. Okay, so I'm subbing this in for our x. Add in for our x. Okay, 2 minus u. And I have to redo our bounds. So when x equals 1, u is 2 minus x, so 2 minus 1 equals 1. And redoing this bound, when x equals 2, u equals 2 minus 2, which is 0. So again, this is the phenomenon that I'm talking about. So we went from bounds of 1 to 2 to bounds of 1 to 0. Upper bound is 0. right? So that means down here, upper bound is 0, lower bound is still 1, coincidentally. Because when you plug in 2 minus 1, you get 1 still. 1 to 0. Notice that. We got to come back to that. That means the whole thing, we're just going to make it from 0 to 1, make it negative out front. Okay. I hope I'm still talking loud enough. I'm sorry. It's very late. Okay. So x minus 1 became, so our x is 2 minus u. But then we need minus 1. So this becomes 2 minus u and then minus 1 is what that whole thing is, right? Because this part is x. Okay. And then our root u, and then our dx was negative du. So then we got a negative du here. So I would suggest we bring this guy out here. Okay, so let's tidy it up a little bit. Negative from 1 to 0. All right, 2 minus u minus 1 really is just 1 minus u, right? Because we can take 2 minus 1 and say that's 1. So we can say 1 minus u times square root u du. Okay, and then also remember we had square root, integral from b to a of f of x dx. Don't know why that x is so big. Equal to the negative integral from, if that was from b to a, this is from a to b, right? So notice you can switch the bounds and change the sign, and it's equivalent. So that's what I'm going to do here. I'm going to switch the bounds and then change the sign again. So it's going to be like a negative integral from 0 to 1, right? Obviously those two negatives are going to cancel each other out. And again, we got to distribute this. U to the 1/2 minus u to the first times u to the 1/2 is u to the 3/2. U to the 3/2 du. So it's going to be integral 0 to 1 u to the 1/2 3/2. I think I'm going to not finish this whole thing because you can kind of get the gist. So u to the 3/2 over 3/2. This is a u. It looks kind of sketch. Minus u to the 5/2 over 5/2. All this evaluated between 0 to 1. Also note that yes, often when you plug in 0 to these things, you get out a 0, but be really careful because sometimes you don't. Sometimes it's like, u plus 1 quantity to a number or x plus 1 quantity to a number. So don't assume that just because you have a 0 here, don't just assume that when you plug it in, you're going to get a 0. All right, so you guys can basically finish it yourself, but seems like it's going to be like you plug in a 1, right? You get 2/3 times 1 to the 3/2 minus 2/5 times 1 to the 5/2 minus, there's a lot of negative signs going on here, 2/3 times 0 to the 3/2, which yes, in this case, these two things are going to be 0, not 1. 0, 5/2. Right, so this should end up being, right, These two end up canceling to 0, but don't take that for granted. It's not always going to happen. And 2/3 minus 2/5, which is, oh, so that is 10/15 minus 6/15, I think. 4/15. Okay. That's it for, well, so the rest of 5.5, read over page 341 yourself, please. Integration of even and odd functions. Just how, like, if you have an even function, very important, that's an integral of an even function that's centered around the origin, where your bounds of integration are centered around the origin. Essentially, you can take the integral of the function just between 0 and the upper number, or the lower number and 0, and double it to get the whole integral. And if it's an odd function, again, with an integral centered around 0, then the two sides, you got a positive side, you got a negative side, they have equal areas, they're going to cancel to 0. It also reviews what is an even and odd function. I think it does. Right? An even function is when you plug in negative x for the input and the output is just the normal f of x. Even function is when you plug in negative x for the input and the output is negative f of x. Like rotational symmetry versus just like normal symmetry. Okay, look at that yourself. And look at the homework solutions online if you need help with the solutions online. We already did 5.6 with the trapezoid rule stuff. I will be back. My next videos are going to be on 5.7. That's fairly difficult. 5.7, I love 5. What are we even on? Yeah, I love 5.5 and 5.7. 5.7 might be my favorite overall section in the whole book. Chain rule's awesome too, though. These are closely related. Anyways, I hope you're having fun. I hope things are going well in your life. Yep. And I will, quote unquote, see you back when we're doing 5.7. All right. Godspeed.